Hi, welcome to the Chapter 13 review questions for Discovering Design with Physics. As usual, we're going to skip these first definition problems because you can easily find them in the book. And we'll start with question 2. So we're identifying the type of charging that was done in each situation. And the first one is that a negatively charged rod is used to give a negative charge to a metal box. So this one's going to be charging by conduction. And that's because it gives the object the same charge as the item in which you are charging it. For B, a glass rod is rubbed against silk, making the glass rod positively charged. This is going to be triboelectric charging, and that's because it involves rubbing two objects together. For question C, a negatively charged rod is used to give a positive charge to a metal box. So this is going to be charging by induction. The object is being given the opposite charge compared to the item with which you're charging it. For question 3, in which of the three cases above did the rod and the other object definitely not come into contact with one another? And they definitely didn't come into contact in 2C because when you charge by induction, it requires that the charged object not touch the object being charged because otherwise those charges do move over. For number 4, so going back to 2B, what charge did the silk develop? The silk is going to become negatively charged, and that's because if the rod became positive, it had to lose electrons. And so because it did become positive, it lost electrons, and those had been transferred to the silk. For question 5, I'm not going to directly give you that one, but if you don't remember from the book, it's on page 362. For question 6, a particle has a charge of 15.7 microcoulombs. How many coulombs is that? So new in this chapter, we are requiring that you know what the prefix, this mu prefix, which stands for micro, means, which is 10 to the negative 6. So all we need to do here is just convert the microcoulombs to coulombs using this value. We have 15.7 microcoulombs, and we're going to multiply that using the conversion factor. So we have 10 to the negative 6 coulombs over 1 microcoulomb. And we'll get 1.57 times 10 to the negative 5, or you can have 0.0000157 coulombs. Okay, either of those. So it is 1.57 times 10 to the negative 5 coulombs. For question 7, a particle with a charge of 15.0 microcoulombs is placed 19.0 centimeters away from the particle with a negative 99.0 microcoulomb charge. What is the force that exists between them? In what directions are the particles accelerated by the force? So for this, we're going to need to use equation 13.1, which is that our force equals our K value times our first charge, our second charge, divided by the radius squared. So this is Coulomb's law, and K is our Coulomb's constant, and you are given that, and you'll be given that for any exams too. And so if you didn't notice it, it's at the top of the first page of the set of review questions if you're going off of this printed out thing, and it's also in the book. Okay, now this constant is in newtons times meters squared divided by coulombs squared. And you notice that our given values are in microcoulombs and our radius is in centimeters. So we're going to need to convert all of that. And I'm just going to kind of do that on the fly because by now we should be pretty familiar with converting. So I'm going to go ahead and just write out our equation. So I'm getting this Coulomb's constant from that first page, 8.99 times 10 to the 9th newtons times meters squared over Coulomb squared. All right. And for me, the simplest way to do the conversion from microcoulombs to coulombs, because we're not at the end and we don't need anything in not accurate, but correct scientific notation, is just to tack on a times 10 to the negative 6 at the end. So I'm just going to write 15.0 times 10 to the negative 6 coulombs, and it'll give us the right answer. This isn't correct scientific notation, but it doesn't matter because we're just in the middle of calculating it. Then times negative 99.0 times 10 to the negative 6 coulombs. And divide that by 0.190 meters. So that's 19 centimeters, converting that into meters squared. Okay, so when I calculate all of that out, you're going to get a, because I used a negative, you don't have to use a negative, as Dr. Wile says, but if you did use a negative, you can. You're going to get negative 3.70 times 10 to the squared newtons. And just like, let's just double check our units here, right? So we're going to have meters squared, and that cancels there. Our coulombs times 2 coulombs times coulombs squared, and so you are left with newtons. Now, this negative just tells us that the charges are attracted to each other. So that means that the force between them is not a negative newtons, right? Is 3.70 times 10 to the second newtons. The 15.0 microcoulomb charge pulls the negative 99.0 microcoulomb charge. We aren't given a left or right here, so we're just going to say toward it. And the negative 99.0 microcoulomb charge pulls the 15.0 microcoulomb charge toward itself. I really should say this itself also. Okay. So that is that one. For question 8, two equal charges are placed 47.6 centimeters from one another. They are pushed away from each other by a force of 196 newtons. What is the magnitude of each charge, and do the charges have the same sign or opposite signs? So you can answer this last question without even doing any calculations. Do the charges have the same sign or the opposite signs? They're definitely going to have the same sides because they are being pushed away from each other. And so if they had opposite signs, they would be being pulled towards each other. For the rest of this, we can put in Coulomb's law, and we are solving, of course, for the Q's, what those charges are. Let's write out Coulomb's law, and then we will rearrange it to solve for that. So our force equals our Coulomb's constant times, instead of saying Q1 times Q2, we're just going to say Q squared because they have the same charge. And divide that by the radius squared. So now we're going to solve for Q here. So we have force times radius squared divided by K. That's going to leave us with Q squared. So we'll take the square root of all that, and that equals our Q. So let's plug everything in here. So our force is 196 newtons times our radius squared. Now we're given those radius in centimeters again. We need to convert that. So 0.476 meters, and square that, divided by our constant, 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. Okay, and then of course we're going to take the square root of all of that. If you wanted to, you could take this out of here and just take the square root of 196 newtons divided by Coulomb's constant, and then just multiply it times 0.476 not squared, and that would do the same thing, but I just have it all under the square root. Okay, so when we calculate all of that out, we're going to get 7.03 times 10 to the negative 5th coulombs. And now we can write out our answer. So each charge is 7.03 times 10 to the negative 5th coulombs, and they are the same sign. For question 7, a helium ion has a nucleus whose charge is 3.20 times 10 to the negative 19th coulombs. Its single electron, which has a mass of 9.11 times 10 to the negative 31 kilograms, and a charge of negative 1.60 times 10 to the negative 19th coulombs, orbits the nucleus with a radius of 2.65 times 10 to the negative 11th meters. What is the speed of the electron in its orbit? Because we are using orbit here, we are going to need to use centripetal force. So this is way back from chapter 7, equation 7.3. The centripetal force equals mass times velocity squared divided by the radius. Okay. Along with that, because we are working with charges, we're going to use Coulomb's law, which is the equation that we've been using for the last two questions. So force equals K times Q1 times Q2 divided by the radius squared. So we're going to set these two forces equal to each other so that we can solve for speed, the velocity here. So we have mass times velocity squared divided by the radius equals our K times Q1 times Q2 divided by the radius squared. So of course one of these radius can cancel. And we are solving for velocity. So we can go ahead and divide by mass on this side and then take the square root of all that, and we will be solving for velocity. So now we can plug everything in. So our constant, 8.99 times 10 to the 9th newtons times meters squared divided by coulomb squared times 3.20 times 10 to the negative 19th coulombs, taking the first charge. Then our second charge is this electron. So it is, that's right here. I'm not going to put the negative this time. 1.60 times 10 to the negative 19th coulombs. And dividing all of that by our radius, which is 2.65 times 10 to the negative 11th meters, times our mass, right here, 9.11 times 10 to the negative 31 kilograms. So let's look at our units and what's canceling. So our coulombs will cancel. And I forgot, make sure we have our square root symbol. Okay. And remember that we're getting velocity. So we need to end up with meters per second squared. Meters squared per second squared over here. So it ends up with meters per second for the velocity. So we need to, let's convert the newtons into its individual units that make it up. And so for newtons, we have kilograms times meters per second squared, right? So this kilograms is going to cancel, and this meters will cancel, and so we do end up with the units that we're wanting. It's always a good idea to check and make sure you have the units that you're going to need at the end. Okay, so when you calculate all of this out with your calculator, you should get 4.37 times 10 to the 6 meters per second. All right, and so the speed of the electron is 4.37 times 10 to the 6 meters per second. For question 10, a 77.1 millicoulomb charge with a mass of 1.12 kilograms is orbiting a negative 32.8 millicoulomb charge with a speed of 7,750 meters per second. What is the radius of its orbit? So this is very similar to the previous problem. We are just trying to determine radius instead of speed. So I'm just going to skip writing this out and just go ahead and make these equal to each other, and then we'll solve for radius instead of velocity like we did here. Okay, so we have mass times velocity squared over radius equals Coulomb's constant times charge 1 times charge 2 divided by radius squared. So this time we're solving for radius. We're going to cancel out those two. And so we're going to get radius equals our Coulomb's constant times charge 1 times charge 2 divided by mass times velocity squared. Okay, so now let's go ahead and plug in all of our values. So we have Coulomb's constant, 8.99 times 10 to the 9th. Newtons times meters squared over Coulomb squared times our first charge, 77.1 millicoulombs. So let's convert that to coulombs. That's going to be 0.0771 coulombs. Then our second charge is 32.8 millicoulombs. We're going to just ignore the negative. 32.8. Oops. We got to convert that to coulombs, right? So 0.0328 coulombs. Dividing this by the charge that is orbiting, which is the mass of the charge that is orbiting, which is 1.12 kilograms, times the velocity squared, 7,750 meters per second, and all of this squared. So again, let's just make sure our units are correct. We should end up with just a flat meters, right, for radius. So our coulombs cancel. Okay, our meters squared cancels. Maybe not put that 2 there, or cancel out that 2 yet, since we're going to need to still remember to square it. Okay, and then remember we have kilograms times meters per second squared. So our second squareds is going to cancel, and our kilograms will cancel. And so we will be left with just meters. So again, all these numbers, plug them into our calculator, and our output should be 0.338 meters. Radius is 0.338 meters. For question 11, 3 charges are arranged as shown in the drawing on the right. What is the force that the black charge experiences? Okay, so I'm going to kind of label my forces A and B, and that's just going to help me. I'm gonna label them when I write out the equations too. Okay, so my force A, which is the one that is to the left and is going to be pulling my black charge to the left, is, we're just going to use Coulomb's law. Okay, so plugging in Coulomb's constant, 8.99 times 10 to the 9th newtons times meter squared per Coulomb squared times, so our first charge is going to be, we'll go ahead and put our red charge. Okay, and remember this is microcoulomb, so I need to convert it to coulomb, so it's going to be 0.0121 coulombs times our second charge, which is our black charge, and we're not going to put a negative because what we basically know is that these forces are attracted to each other, times 0.0110 coulombs, and dividing that by our radius, which is 1.5 meters, and that is squared. Okay, so calculating all of that out, we will get 5.3 times 10 to the 5th newtons, and that is pulling our black charge left. Okay, force B. Coulomb's constant. Our first charge is, we can go ahead and put our black charge, times 0.0110 coulombs times our red charge, converting to coulombs, 0.190 coulombs. And in this case, our radius is 1.8 meters squared. So for this one, we get 5.8 times 10 to the 5th newtons, and this is right. Okay, so at this point, now you're going to subtract these and determine overall which way is the black charge being pulled, because it is being pulled in two directions, and so one has to win out. And so you just need to assign a positive or negative to direction. So I'm just going to say my leftist pocket is positive, okay? And so we're going to just say force A minus force B equals our force net, right? So 5.3 times 10 to the 5th newtons minus 5.8 times 10 to the 5th newtons, and we will get negative 0.5 times 10 to the 5th newtons, okay? Or negative 5 times 10 to the 4th newtons. Okay, so now when we write out our answer, we're going to take this negative, convert it to direction, and just write out the absolute value of this. So we have that the force is 5 times 10 to the 4th newtons, and because we assigned left to be positive and our answer was negative, we are going to the right. For question 12, 3 charges are arranged as shown on the drawing on the right. What is the force that the red charge experiences? And it gives us a hint. Remember that a perpendicular line dropped from any vertex to the opposite side bisects the vertex angle in an equilateral triangle. Okay, so we can quite easily get what the magnitude of these individual forces on the red charge is. So let's just start with that, okay? I'm going to label this one force A and this one force B. So force A, putting in her Coulomb's constant. Our charges are in millicoulombs again, and I'm not going to worry about positive and negative, so I'm just going to say times 0.0141 coulombs times our red charge, 0.0187 coulombs, divided by our radius squared, which is in centimeters, so make sure we convert that to meters. Calculate all of that out, we'll get 1.40 times 10 to the 8th newtons. For force B, Coulomb's constant times our first charge, 0.212 coulombs. Our second charge, 0.1, I wrote this wrong, 0.212 coulombs times 0.0187 coulombs. Divided that by our radius squared, which is also 0.130 meters. I have an equilateral triangle here. And for this one, we will get 2.11 times 10 to the 8th newtons as our force. Okay, so now that we've done that, we need to figure out the geometry. And we have this diagram here. So we can split this into 30 degrees and 30 degrees, right? But we need to change that to our physics angle, right? And so here would be 180 degrees. We're subtracting 30 degrees. So for force A, it's going to be 150 degrees, okay? So that's what this is from here to here, okay? For force B, now we're going all the way around here. So we're doing 180 plus the 30. And so a force B angle is going to be 210 degrees. So now that we have those, we can get our X and Y components for each of these forces, okay? So let's start with Y. Our AY, we have our force here, 1.40 times 10 to the 8th newtons. And for our Y component, we use sine, and our theta is, I have it right. Okay, is 150 degrees. And we get 7.00 times 10 to the 7th newtons. For B Y component, our force was 2.11 times 10 to the 8th newtons from above, times the sine, in this case of 210 degrees. And we get negative 1.06 times 10 to the 8th newtons. So let's go ahead and add those up now to get our CY. So our overall Y force is 7.00 times 10 to the 7th newtons plus a negative, so minus 1.06 times 10 to the 8th newtons. And we get negative 3.6 times 10 to the 7th newtons. So you might be wondering why I have 3 significant figures here and here, and they're both going to the hundredths place, but then only 2 here and going to the tenths place. And that's because of our tens and exponents here, okay? So this, if we rewrite this, it's actually 10.6 times 10 to the 7th, okay? So if we have them at the same precision here, or with the same exponents, then this is actually only going to the tenths place, and this goes to the hundredths place. So we're left with the tenths place at 10 to the 7th, okay? So that is why we get, so then that kind of makes more sense, right? We have negative 10.6 plus 7 is negative 3.6, and then it's times 10 to the 7th. Okay, so now let's do our X components. AX, taking our force from above, using the cosine now of 150, and we get 1.21 times 10 to the 8th newtons. Or Bx, 2.11 times 10 to the 8th newtons times cosine of 210 equals a negative 1 point. Oh, and this one was a negative also. Negative 1.83 times 10 to the 8th newtons, right? And they both should be negative, right? They're pulling both to the left. So now our Cx, adding these together, negative 1.21 times 10 to the 8th newtons minus 1.83 times 10 to the 8th newtons. We get negative 3.04 times 10 to the 8th newtons. Okay, so now that we have our y and x values for C, we can determine what our C force is. So our C is going to be the square root of our y component, 3.6 times 10 to the 7th newtons squared. Technically there's a negative, but since we're squaring it, it doesn't matter, plus 3.04 times 10 to the 8th newtons squared. So because we're adding, I'm going to do these separately. And so we get 1.3 times 10 to the 15th square newtons plus 9.24 times 10 to the 16th square newtons. So notice I have two different values here. And so this could be written as 92.4 times 10 to the 15th. That was square newtons also. Okay, so we're actually in both cases at the 10th place for 10 to the 15th. So when we add those together, we're going to get 93.7 times 10 to the 15th square newtons, which equals 9.37 times 10 to the 16th. Okay. We're going to take the square root of that, and we get 3.06 times 10 to the 8th newtons is our value for C. Okay, so this is our overall force on our red charge. Now we need to get the direction. Okay, so we're going to have our inverse tangent of our y over x. So our negative 3.6 times 10 to the 7th newtons over x, negative 3.04 times 10 to the 8th newtons, and we get 6.8. Now we are going to be, so let's look at our y and x values. We are negative y and negative x, so we are in quadrant 3, and so we need to add 180 to our value, and so we get 186.8 degrees. Okay, so our final answer is that the force is 3.06 times 10 to the 8th newtons. That's what we got here at 186.8 degrees. For question 13, list the 4 rules that electric field lines follow. I'm not going to give you this because these are some of our very important things that you should have memorized for this chapter. And so if you don't have it memorized yet, look on page 359 for Faraday's rules. For question 14, do electric field lines actually exist? And that answer is no. They're useful in visualizing the field, but they're not real. Question 15, does the electric field actually exist? And of course, that answer is yes. That's what we demonstrated in experiment 13.2 for this chapter. For question 16, so we have the electric field generated by 2 stationary charges shown on the right. What is the sign of charge A? So charge A has lines pointing away from it, so that means it's going to be positive. Then for B, the lines are all pointing towards it, so this charge is negative. For C, if the magnitude of the charge on B is 16 millicoulombs, what is the magnitude of the charge on A? So for B, if you count all of these lines that are going into B, there are 16 lines. Going from A, there are only 4 lines. So from a magnitude perspective, the charge on A is 1/4 of what B has. So if B has 16 millicoulombs, A will have 4 millicoulombs. For D, using up, down, right, and left, describe the direction of the acceleration a positive charge would have if it were placed at C. So positive charges are just going to be accelerated in the direction of the nearby electric field lines. Okay, so if we stick a positive charge here, it's just going to accelerate in the same direction as the field lines that are around it. And so for D, or I should say for C, this location, if we put a positive charge here, it's going to accelerate down and to the right. Okay. For E, using up, down, right, and left, we're going to do the same thing for a negative charge at D. So for a negative charge, that's going to accelerate opposite of the nearby field lines. And so it's going to be going up and to the right, okay? Like so. For F, is the magnitude of the acceleration caused by the field greater at C or D? So the answer is going to be D, and that's because the force is proportional to the number of field lines that are in the area, okay? So in D, there are a lot more field lines in close proximity to it than C, okay? Now the question is about acceleration, but force equals mass times acceleration. So if force is proportional to the number of field lines, so of course is acceleration. And so the answer there is D. For question 17, we have another electric field with 4 stationary charges this time. And we're asked to answer these questions. So which of the charges are positive? So positive charges are going to have those electric field lines pointing away from them. And so the ones that have them pointing away are B and D. What can we say about the magnitude of all four charges. So when we're talking about magnitude, it has to do with how many electric field lines are going to and from those charges, and they are all equal. If you count each one, they're all going to be exactly the same, and so we can say that the magnitudes are all equal. For C, what would be the magnitude and direction of the force a positive charge would experience if it were placed at E, which is the midpoint of all four charges? And it's in the middle of all of these charges that have the same magnitude in opposite directions. So B and D are positive, A and C are negative. And so they're all going to cancel out, and your total charge on E is going to be 0. For D, the magnitude of the electric field at X and Y is measured, so here and here. One of them is 15.0 newtons per coulomb, while the other is 25.0 newtons per coulomb. Which is which? So the electric field at X has to be the 25.0 newtons per coulomb. And that's because there's more lines at X, okay? There are much fewer lines close to Y, and there are more at X. And so there's more force happening here at X. So just like in question 16 and that last problem, where these lines, the number of them shows the magnitude of force. So there's more force going on here than at here. And so this is the higher number between the two, and so this higher number has to be the X value. And the electric field must be larger there. For E, a charged particle is placed at point Y and experiences a force of 7.6 newtons down and to the right. What is the charge on the particle? So for this one, we're going to be using equation 13.2. And just write that out. The force equals the charge times E. And remember that E equals the vector that represents the electric field. So our force is 7.6 newtons, and our charge is our unknown. What is our charge? We do have the electric field. I think this question is a little bit confusing because it isn't directly referring us back to the previous one, but we've been given the magnitude of the electric field above, and it was 15.0 newtons per coulomb. Okay, so we're solving for Q. So our Q equals our force divided by our vector representing the electric field. And so that is force 7.6 newtons divided by 15.0 newtons per coulomb, right? And we'll be left with coulombs. And we get 0.51 coulombs. And this is going to be, so the charge is going down and to the right, which is opposite of what these lines are doing. And so, because the lines are pointing up at this point and to the left. And so our charge then is going to be negative. Okay, so the charge is negative 0.51 coulombs. For F, a 0.500 coulomb charge with a mass of 156 grams is placed at point X. What is the magnitude of the acceleration that it experiences? So we're going to use equation 13.2 again. And first we're going to get the force, right? So our force equals, we're given the charge, so Q is 0.500 coulombs times, and we're referring back again to D, where we were told that the electric field at magnitude of the electric field for X was 25.0 newtons per coulomb. Okay. And so the force we will get is 12.5 newtons. So now we can use force equals mass times acceleration to determine what the acceleration is, right? And so our acceleration equals force divided by our mass. So that is going to be 12.5 newtons divided by our mass. We're going to convert that to kilograms, so 0.156 kilograms. And we'll get 80.1 meters per second squared. So question 18, electromagnetic waves cannot travel inside an object. Is the object most likely made of a conductor or an insulator? So this one is going to be a conductor because there's no electric field inside a conductor, and so electromagnetic waves have nothing to vibrate, and so they can't travel inside that object. For 19, suppose you made an electroscope like the one that you made in experiment 13.1, but in this case you used a paperclip covered in plastic and used strips of plastic instead of strips of aluminum foil. Would the electroscope work? Why or why not? So it would not work, and that's because our electroscope worked because electrons could move around in the paperclip and the foil. They can't do that in plastic because it's an insulator, so it's not going to work.